Hello everyone. Let us relook what all things we have covered. That is in the module 4th. So this is module 4th, which is having two parts, quantum mechanics and lasers. We have taken up the lasers module. Okay. So in this case we have seen introduction and what is the abbreviation, light amplification by stimulated emission of radiations, and the basic principle is it is the absorption is the basic principle, and the emission are of two kinds. So we have E1 level and E2 level, that is energy states E1 E2. Then the energy gap is delta E minus E is the delta E that we have equated as h nu. So h nu in turn we can write it as hc divided by lambda by substituting nu, that is a frequency, that is equal to c divided by lambda. So this is what the basic principle. If I supply energy greater than or equal to delta E, if I supply the energy greater than or equal to delta E, then the atoms in the even state, they are going to excite to the higher state, and then when they'll come back to the lower state, that will emit the light. So altogether that light interfere and output as a, we will get the laser as a output. We have seen interaction of radiations with the matter. There are three ways in which light will interact with the matter. That is, first one is induced absorption, second one is the spontaneous emission, third one is stimulated emission. First case, induced absorption, in which the ground state atom will go to the excited state by absorbing the photon of energy h nu, and it will go to the higher energy state, excited state. So this is the absorption case, and then it is absorbed. Now it has to emit. Okay, so how we will represent this? Atom plus photon, that is equal to atom star. This is the absorption. Second one is spontaneous emission. In this case, this we have to consider the uh, absorbed atom, that is atom star. Excited atom we should consider. It will emit the radiation by voluntarily it will emit, that is emitted radiation h nu, what all things it has absorbed, it is going to emit. So this process is called as a spontaneous emission because it is happening spontaneously. It is absorbing and then it is emitting the h nu. So here the equation can be written as atom star is equal to atom plus photon. The excited atom is represented as atom star. When it undergoes the spontaneous emission, we will get back the atom plus one photon will be emitted from the atom. Third one is stimulated emission. So in this case again we should consider, that is before emission we should consider the atom star, that means excited state atom, and here it has to absorb a photon, it should be stimulated by a photon, and then it will emit two photons. Okay, that's why the name itself says it is the stimulated. We are stimulating, we are adding the extra h nu to stimulate the process and to make the atom to come to the ground state. When it come back to the ground state, we will have two h nu, that means two photons we will get. One is stimulated photon and there is incident photon. So this is the stimulated emission which we have seen, and we have seen few definitions, that is population of energy level. That means we can say the number of atoms in that particular state is the population of that particular energy state. So that is the population of the energy state or the energy level. Now population inversion. Okay, if the higher energy levels population is more than the lower energy population, it is called as population inversion. Okay, and we have this Boltzmann's factor, okay, which we have used in the derivation, that is n2 divided by n1, which is the populated inversion case, is equal to e to the power minus h nu divided by kt we have considered. Okay, so where n1 is population of E1 state, n2 is the population of E2 state, k is the Boltzmann's constant, and T is the absolute temperature. This equation we have used in the Einstein's density equation. Okay, where simply we have taken it as e to the power h nu divided by kt. Okay, what is h nu? H nu is the incident photon. Okay, what is that equal to? It will be E2 minus E1, that is delta E. Okay, that means it's a simply energy can be replaced with h nu, so that we have used, that is called as Boltzmann law or Boltzmann equation, that also already we have used in that. So in while teaching I have taken the uh, coefficients first, and then we have replaced this Boltzmann equation in that. Okay, so we have the Einstein's coefficient. There are three processes. So corresponding to three processes we have the three coefficients, right? That is induced absorption case. In that case this depends on two things. One is n1, that is population of the ground state, and then we are supplying this energy h nu, that is energy density we are supplying u nu, that we have to substitute that, that is proportional to both the things: number of atoms present in the ground state n1, energy density of incidence radiation, that is u nu. So we have to take the proportionality of this, that is rate of induced absorption is proportional to n1 and u nu. Proportionality constant is replaced by b12. Okay, b12 n1 u nu is the rate of induced absorption. Similarly we have seen, so in this case b12 is the proportionality constant, that is called as Einstein's coefficient for induced absorption. And second one we have seen the spontaneous emission case. Okay, so in this case the spontaneous emission, this depends only on the number of atoms present in the excited state. That means n2, population of E2 is n2, that depends only on n2. So proportionality is only n2. Therefore rate of spontaneous emission is equal to a21 n2, where a21 is the proportionality constant, is called as, it is the Einstein's coefficient of spontaneous emission. Fine. Then third one, the last one, is stimulated emission case. Now stimulation depends on two things again. So what are those two things? How many numbers of atoms are there in the E2, that means number of atoms in the E2, that is the population of E2, that is n2. Okay, number of atoms present in the excited energy state, that is n2. Then again we are supplying here, we are supplying this energy density, that is u nu. So it depends on two things, n2 and u nu. The rate of stimulated emission therefore can be written as, it is b21 n2 u nu, where b21 is proportionality constant and it is called as Einstein's coefficient of stimulated emission. And then we have seen the equation for energy density in terms of Einstein's coefficient. So what it says is absorption is equal to emission. Okay, we have one kind of absorption, that is rate of absorption is equal to rate of spontaneous emission plus the rate of stimulated emission. So we need to substitute all the equations in these particular rate equation and then go on solving. Okay, then this is all simple mathematics which we have to solve. So we have to use the Boltzmann law here. So substitute that, and some of the modifications we should do in the equations to get the final equation. So we have to equate that, we have to compare that equation with the Planck's law. Planck's already found this equation and we should equate that. So both equation number 6 and equation number 7 are similar. So which all things are equated, we already have discussed that, and we need to find out the final equation, that is energy density equation. Okay, and some derivations, some terms we have seen, that is what is pumping. Pumping action means supplying the energy to the material is called as pumping. What is lasing? What it is emitting, it is called as emission, that is lasing. Active medium, that means what we are filling inside the cavity, it is called as active medium. Then that is the laser cavity. Laser cavity is where we fill the active medium, and it is fitted with the two mirrors. One is fully silvered and there is partially silvered. Okay, when we supply excitation source to that, all the atoms will go to excitation and start emitting the laser. So this is the basic schematic diagram of the construction of the laser, and this L is the length of the cavity. So that depends on the wavelength of the radiation. Okay, we cannot take any number, simple, whatever the distance, that is fixed as L is equal to m divided by 2 into lambda. Okay, so at this condition itself there will be constructive interference. Okay, so from this equation we can find out what is the wavelength also. Now what are the requirements? There are four requirements, main requirements. Those requirements are, first one is we need the source for the pumping action. So there should be excitation source. So excitation source may be light source or maybe electrical energy. We can supply current and make the gases to excite and emit the radiation. So there are examples, there are so many examples. Carbon dioxide laser is there, and then helium neon laser is there. So these are called as gas lasers. In that we use the electrical pumping. And ruby laser is a crystal. Ruby is a crystal where we use the optical pumping, or light itself is the cause for the pumping. So second one is population inversion. That means higher state atoms are more than the lower state, and there should be active medium. Without that we cannot lase it. Then fourth one is lasing cavity. Okay, we need the cavity to fill the active medium. So what are the conditions? Here we have seen the metastable state. Okay, so that state should be achieved. So we simply have seen only E1 state and E2 state, lower energy and excited energy. So in this excited state, atoms will not stay back there for longer duration of time. So those will come back quickly to the ground state. So we had to make them to stay for longer duration of time and then emit the radiation. To make that, to make the population inversion to happen, so when there are more and more atoms in the excited state, we call it as population inversion. So in the simple case, in the E1 and E2 simple case, so there will not be more and more atoms in the excited state. We will never achieve the population inversion. So for that the we have to create the metastable state. We have to add some other material to create E2 state, so that in that state atoms will stay for longer duration of time, and all the atoms are collected over here, and there is a population inversion achieved between E1 state and E2 state. So in the beginning all the atoms will go to excited state. That means in the E3 state it will go, and then those will transmit to the E2 state and collect over here, so that there will be population inversion achieved between E1 state and E2 state. And then at a time at the time where there is a achievement of population inversion, lasing will takes place. That means emission, stimulated emission will takes place. So this state wherein the atoms stay back for longer duration of time, that is 10 to the power 3 to 10 to the power 2, it is called as the metastable state. Now we have two constructions of lasers. Now actually we have to go for construction of carbon dioxide laser and then semiconductor laser. So in this case we have the basic principle. Okay, how the molecules vibrate, what happens, what causes for the emission. Then construction of the carbon dioxide laser, this is the construction. So there are different components put together. We have to construct the carbon dioxide laser. So basic thing we have seen, there should be lasing cavity, there should be excitation source, and there should be medium. Okay, so those basic things we had to see. And we have the working. So principle we have seen, construction, and then working. There are three things: principle, construction, and this is the working, how it works, what makes it to laze. So this is the principle, construction, working of the carbon dioxide laser. Now this is semiconductor laser. Here also we have a principle, construction, mainly gallium arsenide laser. So how it is constructed, what all the components we have to use, and then working of that. So this is the working where you have to draw the band diagram. PN junction band diagram is there, and we have to just go through this electrons and holes, what happens with that, those will recombine or what. Then we have to see the lasing action in that. At the end we have application part. There are two main applications of lasers: data storage application, how the data is stored inside the CD, that means compact disc, or DVD. What is the principle? Then we have the defense application. In the defense, where all we use, mainly they use to find out the distances of the target to shoot that. So they use the target, it is called as the range finding application. So this much we have in the laser topic.